Good morning, everyone. Glad you can join me again. Here we are beginning chapter 13. Chapter 13 is going to be divided into two lectures only. This is one of our short chapters. So, on chapter 13, we're going to cover solids and modern materials, keeping in mind everything we learned about intermolecular forces that bring these particles together to make them into a solid. Only two objectives, but a lot of sub-objectives. So the first thing we're going to cover is learn how to classify and organize solids. We're going to organize these solids and classify them based on their bonding and intermolecular forces. There's going to be three main types: molecular, ionic, and atomic. However, the atomic can be non-bonding, it could be metallic, or it could be a covalent network. And then we're also going to describe the difference between crystalline and amorphous solids. When we go into the understanding how these solids create networks, which we call lattices, the book gives you a lot of information. Most of that information you will never see it again, so we're going to focus on the important things. So we're not going to talk about the lattice points, the angles, the radius, or anything like that. We're not going to talk also, either about the tridimensional types, the 7 three-dimensional types. We're going to concentrate our efforts in understanding the body-centered unit cell and the face-centered lattice unit cell. And we're also going to see the electron beam model to be able to understand a specific type of solid, which is the metallic solid, to be able to understand why solids are conductors of electricity and heat, why they are ductile and malleable, and all that. And for that, we're going to use the C model theory. And at this point, we will not be using the molecular orbital theory because I'm going to be talking about that later. Most of the time, we're supposed to cover that on 1411, but we rarely have time to get to that. So I'm going to assume that none of you have ever been exposed to the molecular orbital theory. And then before we leave the first objective behind, we're going to see how by looking at the unit cell, we can predict the empirical formula or the formula of the compound. From there, we will move to our second objective, which is semiconductors. And we're going to see how to understand this. This is basically what drives our current technologies. So this is very important to understand. And we're going to talk about the valence band, the conduction band, the band gap, and the conductors that are going to be N-type or P-type. And we're going to see what makes a substance a conductor, a semiconductor, or an insulator by talking about the band gap, and we're going to see how by looking at the elements and the position on the periodic table, we can predict the relative size of the band gap and therefore the conduction properties. And then we will briefly talk about what is a p doping and n doping, positive doping and negative doping. So let's begin with the first one. That makes sense. Classify and organize solids. So like I told you before, three types: molecular, made out of molecules; ionic, made out of cations and anions; and atomic, just made out of atoms by themselves. And the atomic can be non-bonding. So basically the attraction is dispersion forces, or dipole-dipoles, or hydrogen bonding. Or it could be actually, let me correct myself. If it's atomic, it cannot be a dipole-dipole. Dipole requires a molecule. The metallic, whenever you have a metal from the periodic table, and the covalent network, where you have non-metals elements making a network. So let's begin with some of these problems. So, which of these structures, and he's talking about this one versus that one, represents an amorphous structure? An amorphous structure means that it doesn't have a very defined structure. If you notice, this one here, have a very defined edge, almost like a 90-degree edge. So that wouldn't be amorphous because you have a very, very defined edges on some of the sides. In contrast, this one, there's no defined form for that one. So this one would be, the amorphous one, and then the one that is not amorphous, we're gonna call it crystalline. And the crystalline, if we look into a molecular level, we're gonna see that it have a very defined pattern, and that pattern continues in a 3-dimension setup. Meanwhile, the amorphous, there's no pattern. You got a bunch of different forms attached together, not like this one where everything is the same. So at the molecular level, the crystalline will have a very defined pattern. The amorphous will not have a very defined pattern. Having a very defined pattern means that you're gonna see structures like this, where you have straight lines, 90-degree angles, and so on. So now let's talk more about how we're gonna identify what type of solid we're talking about. So once more, we're gonna say molecular, ionic, or atomic. Let's talk about molecular first. Back on 1411, we learned that molecular could be two elements joined together, the same, that would be a molecular element, or it could be two elements joined together, different ones, that would be a compound. But it requires at least two of them bonded together. So that would be a molecule. An ionic compound is going to be a cation with an ion. So it would have to be a metal with a non-metal. Remember that from Chem 1 or Chem 1411? And then the atomic is just going to be atoms not bonded together. So they are not bonded together. So all we're talking in here is intermolecular forces with one exception. So atomic could be non-bonding, like this one. It could be metallic, let's say iron, joined with iron, but remember we have a new theory to understand metals, so we're not talking covalent or ionic. This will be a whole new concept, but it's basically metallic atoms joined together in their own specific way of doing it, with the C model and so on. So if this was, for example, chlorine, that wouldn't be metallic because chlorine is a non-metal. And then we have the covalent network. Covalent means a non-metal attached to a non-metal. So that would be when you have, for example, carbon, which can make 4 bonds attached to another carbon, which can make 4 bonds. This one is attached to this carbon, which could be attached to this carbon, and you see how we start making like a network. But all of them are non-metals with non-metals, or covalent networks. So let's apply this to these problems that we have here. So argon, if I have a bunch of argons together, because it's a solid, right? So it has to be a bunch of them together. So if I have a bunch of argons together, would that be molecular? No, molecular requires that they are bonded together. And argon is a noble gas, it's not going to be bonded to anything, at least to the level we study here. So it cannot be molecular because we're dealing with a noble gas. Can it be ionic? No, ionic needs a metal and a non-metal. It cannot be ionic. So therefore, it has to be atomic. And I just told you, this is a noble gas. It cannot bond. So this is going to be a non-bonding atomic solid. The only thing keeping it like a solid together is the intermolecular forces. And as you learned on chapter 12, probably there's a lot of pressure put into it to make it into a solid. Remember the phase diagrams? If you put a lot of pressure, then you can make it into a solid. The higher the pressure, the more the possibility of being a solid. So this would be non-bonding atomic solid. So that's what we would have on that case. What about the next one? K2O. Well, we know that we have K, which is positive, and we have oxygen, which is negative. So that means we need another K to balance that. So K2O. So positive and negative, this will be ionic. This will be an ionic solid. And how would that be a solid? Well, you're going to have another one where you have a O2 there, another K plus, so the oxygen, right? Which means you're going to have another K there, which means you're going to have another K there. So you see how a pattern is developed, and it's not bonded. What is keeping them together is the positive and the negative coming together, but it's not bonding by sharing electrons. So that would be ionic. And the solid would be thousands and thousands of them coordinated in such a way. What about the third one? Water, H2O, where we know that water is going to be like this. We know that water is a dipole, remember? So water can be combined with another water by a dipole-dipole interaction, and you can continue having more waters there, more waters there. So basically what we have is a molecule being attracted by intermolecular force to another molecule, being attracted by intermolecular force to another molecule, and so on. So this is what we call a molecular solid. Notice the difference between this one and the potassium oxide. The potassium oxide is ionic. You can see that that's a metal with a non-metal. So the water is molecular. Two non-metals coming together, attracting other molecules like itself, making a solid. And then we have the iron. And what we have here is, like I showed you before, iron with another iron, with another iron, with another iron, and so on, forming a solid when they come together. So this is just one, right? So this is just an atom, but it's a metal. So this is a metallic solid. So let's do a quick review. How do I know if I have a molecular solid? Well, you're going to have a molecule. What is a molecule? Two or more atoms bonded together. And if they're bonded together, that means that they are covalent, like water or something like that. What about a ionic solid? On an ionic solid, you're going to need a metal with a non-metal. What about the atomic solid? Well, the atomic solids are going to be three different types. Non-bonding, and that most of the time, almost 100% of the time, is because you have a noble gas. Metallic, you need a metal. So the metal has to be there, and only metals. And the covalent network, most likely you're going to have an element, a non-metal, because it's a covalent network. You're going to have an element with multiple places to attach, making a network, and so on and so on. Gallium may probably do that also. So remember, it will be non-metals combining continuously because they have a lot of attachment points. For example, if I have, let's say that I have lithium. I know lithium is a metal. Well, let's think for a second that, let's say for a second that it's a non-metal and it have one valence. Actually, let's do it better. Let me do it with this one. This would be a better example. Let's do it with hydrogen. Can hydrogen make a network? No, no way. Hydrogen can only make one bond. So how is it gonna make a network where it's gonna connect with others like itself? That would be impossible because it can only do one bond. So keep that in mind. Remember everything you learned about Lewis structures, valence shells, and all that kind of stuff. So here's your first daily work. Basically the same thing I just did, different compounds. So think about it. Are you dealing with a molecular solid, an ionic solid, or a possible atomic non-bonding, basically an noble gas, metallic, you need the metals, or covalent network where you have an element that is a non-metal that can do a lot of connections. So let's do something else. So once more, now we're looking at this. So what is that? Well, that's the representation of what we call a unit cell. So if I have a solid and I have a bunch of atoms together in there, and if you look at all that combination of atoms, you can say, you know what? I am detecting a pattern. Oh, okay, there's one. Okay, I can see my repeating unit. So I have a repeating unit in here. So that repeating unit is what we call the unit cell. You look for a pattern and you find the smaller possible pattern you can find. If you look at the tutorial videos that are posted in Canvas, there's 3 videos in there that can show you this so much better of what I can show you to you by doing drawings. Go see the computerized images so you can see nicely how to visualize these unit cells. So, but it's basically the smallest pattern you can find on the network that you can see. So this is a unit cell. So does this unit cell represent a molecular solid? Well, a molecular solid that will have to be bonded, and it's going to be a molecule, which is basically a covalent compound. So basically, non-metals with non-metals, we have a metal in there. So no, that cannot be a molecular solid. Can it be an ionic solid? An ionic solid would require a cation and an anion making a network. A cation and an ion. Yeah, most likely this is our answer. But let's continue checking. An atomic solid. An atomic solid contains atoms combined together. And one of them is non-bonding. Obviously, these ones are bonding. So no, that cannot be what we're talking about. What about metallic? Well, it contains chlorine, so it cannot be metallic. Covalent network. Covalent has to be non-metals. There's a metal there. So the answer is ionic solid. This is going to be an ionic solid based on the descriptions on the process of elimination we have used. Is the unit cell body center or face center? So this is a new concept. So once that we have the unit cell, we're going to look at the unit. We are going to visualize it on 3D like you can see on this drawing, and we can say there's a body on the center. So this one is body center. On the faces here, there's something on the center of the face. On the face here, there's something on the center of the face. So you will be tempted to say this is also face center. But what we're gonna focus is you find a body right on the center, then it's gonna be body center. So let's do this daily work. So you're doing this daily work. So this is going on the paper you're gonna upload. But let's do it together so I can review something more. So will this be a crystalline or an amorphous solid? What do you think? When you look at this solid, does it look amorphous or does it look very well defined? Does it look very well defined? Yes, you can see degrees that are very well defined. So this is not amorphous, definitely. This is a crystalline solid. Does this structure represent a molecular solid? Well, this is sugar, and it's telling us their name. It's showing us the structure. So a molecular solid, it would be a molecule attracted to other molecules, So if you look at these molecules here, this molecule is not connected to that molecule. So therefore, what we're talking about is a intermolecular force keeping them together. So this solid where all of these are coming together is because you have intermolecular forces there. So you have a molecule there and a molecule there. So this is basically telling me this is most likely a molecular solid. So why not an ionic solid? Well, an ionic solid requires a metal and a non-metal, and everything you see here is non-metal elements. So that's why it cannot be an ionic solid. An atomic solid, we obviously have a molecule, so that's not an atomic solid. Okay? Remember, you're still doing this one. I just wanted to cover more with you. Is the unit cell body center or face center? Do you see the unit cell anywhere? The concept of unit cell, it's only going to apply to ionic solids or metallic atomic solids. Covalent network, that's just going to be continuous and always the same thing, so there's no such thing as a unit cell. And the non-bonding, that's just being attracted by dispersion forces. So unit cell, save it for ionic solids or metallic solids. So make sure that you finish this, make sure that you set up your own answer for this one. And then you have this one. So what about once we know all that information, what else can we do with it? For example, which one of these out of each pair, which one will have the higher melting point? And if you remember chapter 12, the higher boiling point was given by the one with the stronger intermolecular forces. Therefore, it requires more energy to start moving the molecules, so they will misalign and the intermolecular forces will break apart. So this is melting point, same thing. Now, instead of going from liquid to gas, now it's going from solid to liquid. So once more, intermolecular forces. But we're going to do it different now. We're going to say, okay, so this solid is going to be ionic because you got a metal with a non-metal. This solid, which is all covalent compounds, this is going to have to be molecular. So molecular will be attracted either by dispersion forces or dipole-dipole and hydrogen bonding, where the ionic is going to be attracted by the ionic force, which is the stronger one. Remember that from chapter 12. So it will take a higher temperature to melt this one. So that one will require the higher, that one will have the higher melting point. What about this one here? So this one, krypton, that's an overgas. So this is going to be atomic non-bonding. Versus xenon, which is another noble gas, atomic non-bonding. So the only thing keeping these two together with their respective counterparts is dispersion force. So how do we know which one have the stronger dispersion force? It would have to be the bigger one, right? If all they have going for it is dispersion forces, then the bigger one will have the stronger dispersion force and therefore the higher melting point. So which one is bigger? Krypton or xenon? So remember the periodic table, what would be bigger? It would be krypton, right? So krypton will be the biggest one, so therefore it should have the higher melting point because the dispersion force will be the biggest one. What about the next one? Well, on the next one, we have carbon tetrachloride, which is a molecule, two nonmetals. So this will be molecular solid. And then we have silicon tetrachloride, which is going to be also molecular solid. So when you have molecules, they will have dispersion. Remember when we did the tables? They can also be dipoles. So carbon tetrachloride. That's all even, so it would be non-polar. So there's no dipole on that one. The same with the other one. So the only thing they have going for them is just dispersion. So which one is the biggest one? That would be, this will be the biggest one. Therefore, the one with the higher melting point. Let me take a second to answer something that people usually tend to think. So if I have carbon connected to a chlorine, connected to a chlorine, connected to a chlorine, connected to a chlorine, how come that one is not a covalent network where I have where I will have another carbon connected to a chlorine, connected to a chlorine, connected to a chlorine? Why not? Why not continue doing that? Well, let's erase this before we go crazy. Because we know how to do Lewis structures. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. The chlorines around the carbon, they're already full. They cannot continue the network. So this is just a molecule. You cannot have a network there because nothing can connect to the chlorine. the chlorine already have 8 electrons. So there's no way to continue, so it's a molecule. So it cannot be a covalent network. What about the last one? The last one is, I'm gonna have on the last one ionic and ionic. So both of them are ionics, so be very similar. However, all matter contain dispersion. So what would be the biggest one? The biggest one would be, well, let's see, we can do it by mass, right? Sodium is about 21 grams, chlorine is around 35, this is very rough. So about 56 grams per mole. Calcium is more than 21. Oxygen is 16. So 7. So it's gonna be, this one is gonna be a little bit more or so. So in terms of mass, I don't think we can really decide about these two. However, we can find the electronegativities and we can see which one would show a bigger difference in electronegativity. That one should be the one with the stronger attractions. And that one will give you the one with the higher melting point. So go ahead and do the same things, same logic, compare everything, and decide which way you're gonna go. Think about the type of solids you have. Think about the intermolecular forces involved in those type of solids, and the stronger the forces involved, the higher the melting point. So let's go back to the unit cell. So first thing, determine if this figure represents an ionic or a molecular compound. Molecular compound non-metals with non-metals. So this one is definitely ionic. You have a metal and a non-metal. Determine the coordination number of zinc. So what is that? Coordination number is nothing more than how many things are bonded to it. So we're looking at zinc. So this zinc have, let me change colors, have 1 chlorine attached to it, 2 chlorines attached to it, 3 chlorines, 4 chlorines. So let's double check with another one. 1, 2, 3, and 4. 1, 2, 3, and 4. So everywhere we look, we see the zinc connected to chlorine, and we see that there's 4 chlorines attached to the zinc. So the coordination number for zinc is 4. There's 4 chlor atoms attached to the zinc. So the answer will be 4. What is the coordination number for sulfide? Well, let's take a look at the sulfide then. So the sulfide, let's see, here's 1 and 2. Here's another 1 and 2. Here is another 1. Okay, I'm confused now. So if it's 1 or 2, well, here's another 1 and 2. Here is another 1 and 2. And it appears to be, well, here's another 1. And it appears to be 1 or 2. I don't know exactly which one. And if my answer is, and I would say, well, I have more 2s than 1, So you're going to go with 2. And is that the answer I give you? That's wrong, because I'm not looking at the big picture. What is the big picture? The big picture is that I have this unit cell, which is nothing more like a cube, right? But this unit cell is connected to another unit cell, which 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 is connected. So you see where I'm going with this? So these unit cells are not by themselves. They're making a network of unit cells. So in reality, this sulfide, for example, is connected to 1 and 2 on this unit cell, and then it's going to connect with 2 more on the top unit cell. This one here is connected to 1 and 2, then it's going to connect to 2 more coming to the front. And everywhere you look around, you're going to notice that each sulfide, when you look at the big picture, is going to end up with 4 atoms attached to it. So what we're going to say then is that the zinc is connected to 4 of these, and the sulfide is connected to 4 of those. So we can say then that the formula is, but we know that's an ionic compound. So when we do formulas for an ionic compound, we learn in Chem 1 that we have to simplify the numbers. So in reality, that is the formula. And then we can go way back into 1411 and we say, how did we learn how to write formulas? Well, I memorized that zinc is 2 plus. If zinc is going to lose electrons, it's going to be 2 plus. And when we did electron configurations on 1411, you understood why zinc can only be 2 plus. And sulfide need 2 more electrons to be like an overgas, so then we do crisscross, and we come up with this, which is exactly what we came up with. So now you know better where these formulas are coming from. So the coordination number for zinc on this case is 4. The coordination number for sulfide is 4. When you put it all together, you come out with the same formula we used to come up when we did just crisscross. Crisscross is just a shortcut. Now you understand where these formulas are coming from, especially if we're talking about a solid. And let's see what else we have. So we found that this was 4, and the formula we came up with was, after simplifying, that number there. So apply those concepts to this unit cell and make sure you show your work on how you got to that point. Going back to this one here, another way to find the formula is by counting atoms. What do I mean by counting atoms? Well, let's count the sulfides. How many on this unit cell, how many atoms of sulfide really belong to the unit cell? And you can see this a lot better on the videos that I posted on the tutorial videos. Well, this cell have 1, 2, 3, 4, 5, 6, 7, and 8 atoms in corners. And that's important to realize because this unit cell, this unit cell, right, which is like a cube, is connected to another unit cell, which is connected to another unit cell, which is connected to another unit cell, which is connected to another unit cell. So when you finish doing all that, the only thing of this atom that belongs to this unit cell is only 1/8. There's going to be 8 cubes all around it. So only 1/8 belong to this cubic cell. And there are 8 of them. So all those corners represent one atom only. So what about not the ones in the corners? What about the ones on the, so this is going to be a face, right? So the one on the center of the face, which is also being shared by the one unit cell coming to the front. So half of it is on the unit cell that we want. The other half is on this unit cell that I just drew coming toward us. So that means that for the ones that are on the faces, that one, that one, that one, that one, that one, that one. So since this is like a cube, the cube is going to have 6 faces. So there's going to be 6 atoms on the face. But for this particular unit cell that we're looking at, only half of that atom belongs to it. The other one belongs to the one on top or the one on the center or something like that. So only on the ones that are on the faces, only 1/2 belong to the cell. So this is the same as 3 atoms. So let's take a closer look. Do we happen to have one on the center like you do on this one? This one has one right on the center that doesn't share with anyone else. Do we have one like that on this one here? No. There's a space between these two there. There's nothing in there, so you have no body center. If there was one on the center like this one here, that would be one atom full by itself belonging to this shell, to this cell. So all together, the sulfide represents 4 atoms. What about the zinc? Well, the zinc, they appear to be totally inside the cell. They are not being shared with the other unit cells coming to the top or to the front or to the back. So the zinc, you're also going to have 4. So what did we do? We came up with 4 zincs and 4 sulfides, which give us exactly the same thing. So you can find the unit formula by counting atoms. Remember, the ones in the corners have a value of 1/8 only. The one on the faces represents only half an atom. And if it happens to be body center, that whole atom belongs to that cell only. Or you can do it with coordination numbers. How many atoms are attached to it, but you have to be thinking, is this atom also attached to the one on top, to the one on the front, to the one to the side, to the one on the back? So you can do the unit formula by counting atoms or by doing coordination numbers. So now it's your turn to do this one. And then do that one also. Continue practicing with it. And with that, now we're more familiar with molecular solids, ionic solids, and the atomics, where you can have non-bonding, noble gases, metallic with metals, or if you happen to have an atom that can connect on a lot of places, most likely a network. You see that crystalline solids have very defined edges because they have a very organized structure, and the amorphous, they are all over the place. You saw what a body center structure is once you identify the unit cell, and you know what a phase center is. And we were able to predict the empirical formula by doing coordination numbers and by counting atoms. And the last thing I would like to do before we finish this part of the lecture is to talk about the theory of the C model of electron C model for metallic bonding. So if we have a lot of metals, how can we explain that metals can conduct electricity, can conduct heat, that are malleable, and are ductile? Well, we're going to visualize it like this. We're going to visualize a lot of metals in there, where each one, for example, sodium, have one valence electron. Another sodium, we have another valence electron. Another sodium, we have another valence electrons. And if you notice, they cannot be bonding and doing this lattice because it's only one valence electron. So the way this theory explains metals, and metals is different because metals contain, most of the metals contain d orbitals and so on, is that what's going to happen is these electrons are going to be fluctuating all around the atoms. So it's going to have like an ocean of metals with a bunch of cations on the inside. So from remember the orbitals that we discussed on Chem 1411, they can be moving through all the orbitals. So you can imagine the electrons to be like fluid, being attracted by all the positive nucleus, but kind of belonging to every single atom at the same time. Because of that, you can take a metal and bend it because you are bending like a fluid. Because the electrons are moving, then you can explain electrical conductivity and thermal conductivity. And ductility means being able to stretch it out and get like a small, taking a big chunk of metal and get it really soft and stretch it out like you will do with bubble gum, for example. So it's very ductile. And that you can do because if you imagine the electrons as being like an ocean, you can stretch it out without breaking. There are other properties of metals that we cannot explain. For that, we're going to need to use the molecular orbital model, but I want to cover that first before we try to explain that. So for right now, understand that the electron C model of metallic bonding basically says every single atom of the metal is enjoying the use of all the electrons of all the other atoms, and these electrons are moving like an ocean through the orbitals around this nucleus. And with that, we're gonna stop there. And next time we're gonna continue talking about solid and modern materials, but we're gonna start talking about semiconductors and insulators, and we're gonna have to explain molecular orbital theory, band gap, and so on. So let's leave it there for right now. See you next time. Take care.